Myself, Dinesh, working as assistant professor in physics. In this video, I am going to explain the topic Biprism. Here, what is Biprism? Here, first, Biprism means it is an optical device to obtain two coherent sources from a single source by refraction. Here, it consists of two acute angled thin prisms, that means 30-minute angle, with their bases in contact with each other so as to form a single prism. The obtuse angle of the prism is 179 degree. In practice, a thin glass plate is taken and one of its faces is grounded and polished till a prism is formed, as shown here, with an obtuse angle of about 179 degree and two side angles of the order of 30-minute. Here, these two images illustrate the real biprisms. Let us see the production of fringes in a biprism. How the fringes are formed in a biprism. See here, this is the experimental setup. Here, this one is biprism. S1 and S2 are the virtual sources of the source S. S1 and S2 acts as coherent sources. Here, S is a narrow vertical slit which is illuminated by a monochromatic light. The light from the source S is allowed to fall symmetrically on the prism P, biprism P, placed at a small distance d from the source S, having its refracting edge parallel to the slits. The light emerging from the upper and lower halves of the prism appears to start from two virtual images S1 and S2, which acts as a coherent sources derived from the source S. The cones of the light BS1E, BS1E, here cones of light BS1E and AS2C, AS2C, diverging from the source S1 and S2 are superposed and the interference fringes are formed in the overlapping region B.Sc. Here in this region B.Sc, these may be obtained on a screen or seen through the eyepiece. Let us see the theory of biprism or expression for fringe width. We can derive the expression for fringe width in biprism. See here. Here S1 and S2 are the coherent sources, that means virtual sources which are derived from the single source S. Here the screen is kept at a distance d from the coherent sources S1 and S2. Here the light emerging from the sources S1 and S2 be in phase since they traverse slightly different paths in reaching the point P. Here the light travel from S1 reach the point P and S2, the light from S2 reach the point P. Hence they travel different paths while reaching the point P. There arises a path difference and hence a phase difference between these two. The path difference between light emerging from S1 and S2 in reaching the point P on the screen is S2K. Here S2K is the path difference between the two light waves which are originate from S1 and S2. Therefore, the path difference S2K is equal to d sin theta. Here in this triangle S1 S2K, sin theta is defined as opposite by hypotenuse. That means S2K upon the d, distance between the two sources S1 and S2. Therefore, S2K is equal to d sin theta. Since theta is very small, therefore sin theta is equal to tan theta. Part difference should be d sin theta equals d tan theta. Here you can substitute for S2k part difference. Here d sin theta equals d tan theta. Therefore, in the triangle OPQ triangle, from the diagram OPQ triangle, tan theta equals x upon the d. X upon d. Therefore, part difference should be x into d upon capital D. X into d upon capital D. Here, the substitute the value of tan theta in this equation, above equation, for x by d. Let us see the conditions for bright fringes. Here, part difference should be n lambda. This is the condition for bright fringe. Therefore, part difference, we know that xd upon d equals n lambda, where n equals 0, 1, 2, 3 and so on. For nth bright fringe, from the center of the fringe system on the screen, O is xn equals, here xn, n is the subscript, xn, that is the fringe number, is equal to n lambda into d upon d. Let's suppose xn means 10th fringe. For example, 10th fringe. Assume it to be 10th fringe. Therefore, xn equals n lambda d by d. For n minus 1th bright fringe on the screen, n minus 1th bright fringe means here n 10, 10 minus 1 means 9th fringe. This nth bright means 10th fringe, n minus 1 means 9th fringe. Therefore, xn minus 1 equals n minus 1 into lambda d by d. Therefore, fringe width beta equals the difference of these two, xn minus 1 equals n lambda into d by d minus of n minus 1 into lambda d by d is equal to lambda d by d. On further simplification of this one, we get the fringe width beta equals lambda d by d. Let it be equation 1. Now, conditions for dark fringe. Here, the part difference for dark fringe should be delta equals 2n minus 1 into lambda by 2 or 2n plus 1 lambda by 2, where n equals 1, 2, 3, 4 and so on. For nth dark fringe, let's suppose 10th dark fringe, then it becomes xn equals 2n minus 1 by 2 into lambda d by d. For n minus 1th dark fringe, that means 9th dark fringe. Here above equation stands for 10th dark fringe. Here lower equation stands for 9th dark fringe. That means xn minus 1 equals 2 into n minus 1 of minus 1 divided by 2 into lambda d by d. Let us see the fringe width. Here fringe width means the difference of these two. Here xn minus 1 is equal to, substitute these two equations here, we get, on further simplification, we get lambda d by d, lambda into capital D by d. Let it be equation 2. From equations 1 and 2, we get fringe width beta equals lambda d by d. Hence, all the fringes are of equal width. All the fringes are of equal width. That means the distance between the two dark fringe is also equal to the distance between the two bright fringes. Let us see the measurement of distance between two coherent sources. Here, for the measurement of d, that means distance between two coherent sources, a convex lens of short focal length is mounted between the prism P and the eyepiece. Here, prism and the eyepiece. By moving the lens along the length of the bench, two positions of lenses L1 and L2 are obtained such that at L1 an enlarged real images of S1 and S2, and at the position L2 a diminished real images of S1 and S2 are obtained as shown in the diagram here. This is possible only when the object and image distances are interchanged. The separation D1 and D2 in the enlarged and diminished images are measured. Here in the position of lens L1, here we get D1 by D equals V by U. That means image distance by object distance. Here the image distance is prism to eyepiece, that is the image distance, and the prism to source, that is the object distance, that is V by U. Next, at the position L2, now we can move the lens towards the eyepiece, that is the position of lens L2. Then we get D2 by D, that is equal to the V dash upon U dash. Here when the lens L1, here it is moved towards the position L2, then the image distance becomes V dash, the object distance becomes U dash. Here object distance is U dash, image distance is V dash. Therefore it is equal to U by V. That is V dash is replaced by U, that means U dash is equal to V. Therefore, from these two equations, multiply these two equations, D1 by D into D2 by D equals V by U into U by V, that is equal to 1. On simplification, U get cancelled, V get cancelled, that becomes 1. Therefore, D square is equal to D1 into dt, D1 into D2. Therefore, D equals square root of D1 D2. Let us say the Lloyd's mirror. Here the arrangement for producing an interference pattern with a single light source is known as Lloyd's mirror. Let us see how the phase change produced by reflection method in case of Lloyd's mirror. Here this one is a schematic diagram of Lloyd's mirror, that is phase changer produced by reflection method. Here a light source is placed at a point source S closer to a mirror, and a viewing screen is placed some distance away at perpendicular to the mirror. This one is mirror, this one is point source, this one is viewing screen. Light waves can reach point P on the screen either by the direct path SP, like this, or by the path involving reflection from the mirror, like this. Reflection, here it is incident here and gets reflected. This one is possible. The reflected ray can treated as a ray originating from a virtual source at the point S dash is the virtual source of the real source S. As a result, we can think of this arrangement as a double slit source with the distance between points S and S dash comparable to length D in the figure. Hence, at observation points are far from the source, that means the length is very much greater than the distance between the two virtual sources. We expect waves from the points S and S dash to form an interference pattern just like the one we see from two real coherent sources. An interference pattern is indeed observed on the screen. However, the positions of the dark and bright fringes are reversed relative to the pattern created by two real coherent sources, just like as in Young's experiment. This is because the coherent sources at point S and S dash differ in phase angle by 180 degree, a phase change produced by reflection. To illustrate this further, consider the point P on the screen, the point where the mirror intersects the screen. This point is equidistant from the points S and S dash. If path difference alone were responsible for the phase difference, we would see a bright fringe at a point P because the path difference is 0 for this point, corresponding to the central bright fringe of the two slits interference pattern. Instead, we observe a dark fringe at a point P because of 180 degree upon reflection from the medium that has a higher index of refraction than the one in which the wave is traveling. Fringe width is given by, in this case, should be lambda into d by d as in Young's double slit experiment. Therefore, beta is equal to fringe width beta equals lambda into d by d. Let us see the comparison of interference pattern with biprism. Here in case of biprism, the complete set of fringes is obtained. But in case of Light's mirror, very few fringes on one side of the central fringe are observed, the central fringe being itself invisible. In biprism, the central fringe is bright, whereas in case of Light's mirror, it is dark. This is the main difference. The central fringe is less sharp in biprism, but in case compared to Light's mirror. Let us see the problem section. The distance between two virtual images of a slit formed by a biprism is 0.3 millimeter. If the fringes of width 0.59 millimeter are formed on a screen placed at a distance of 30 centimeter from the slit, calculate the wavelength of the light used. Here data is given here. Here d is the distance between the two sources. Distance between the two sources is 0.3 millimeter here, virtual source distance, that is 0.3 into 10 raised to minus 3 meter. Convert it into SI unit. The fringe width beta is equal to 0.59 into 10 raised to minus 3 meter. The distance between prism and screen d is equal to 30 into 10 raised to minus 2 meter. Then find out wavelength of light used, lambda. Yeah, for this one, you can use the formula, the fringe width beta equals lambda into d by small d. Therefore, lambda is equal to beta into d upon capital D. By substituting above data in this formula, on further calculation, you can get 0.59 into 10 to the power of minus 6 meter. This is the wavelength. Thank you.